This is Garis MPC, Math, Physics, Computing. It's 130 plus courses at Masters and PhD level in pure mathematics and mathematical physics. This is course number 4, so MPC 4 on linear algebra. This is lecture number 1 on vectors in n-dimensional real space and n-dimensional complex space, spatial vectors, and session CC. So we've been through the alphabet already once, and so this is what, the 29th session for this chapter. One chapter, one lecture, one lecture, one chapter. Okay, so we are still in section 2, that's the solve problems section for the chapter. And in the previous session, which by the way, general comment, I'll make mistakes, sometimes things just slip out. My brain memory gets in the wrong groove and I just come out with something that I shouldn't have said. For example, sometimes I'll say greater than when I should have said less than. I noticed, playing back some of the videos, I noticed one time I said, instead of saying the Cauchy-Schwarz inequality, the term Cauchy got me down the wrong memory groove, and I said the Cauchy-Riemann equations. It's probably more strongly reinforced in my brain unconsciously than the Cauchy-Schwarz inequality. And perhaps a bit more seriously, the previous session I said that was the last session of chapter 1. Well, that's mistaken because there are 2 more. There's this one and the next one. So there will be 30. Yeah, total of 30 sessions for chapter 1. Alright, so last session we did part 1 of this question, 1.32. So we're just continuing on. So this is the second part. So we were talking about hyperplanes and normals and such things. So in part 2 we have a hyperplane, just call it H for hyperplane, and you're told that this plane passes through this point, or alternatively this point lies on the hyperplane, okay? And you're told that this hyperplane is parallel, in other words has the same normal, so if my palm here is the hyperplane and the black pencil is the normal, so orthogonal to any vector or directed line segment that lies in this plane. So this vector in the plane and this vector here, they will be orthogonal. That means the dot product is 0. Okay, so you have another hyperplane that's parallel to this H. So imagine, so it'll have the same normal, and the 2 normals are collinear. They lie along the same line. So you might have another hyperplane that's parallel to it, so it might be like that. So you have hyperplane H dashed and hyperplane H with the same normal, right? So the 2 planes are oriented the same way, like that or that. So not the case like that or like that, okay? All right, so now this second hyperplane, whose normal is collinear with the first one, its equation, so you're given the equation of this second hyperplane, and here it is. So here's your equation of your second hyperplane, and you're asked to find what's the equation for the hyperplane, the original, the first hyperplane, H. Well, here's the because symbol. Now, because these 2 hyperplanes, the original and the second one, so H and H dash, because they're parallel, that's hyperplane H, and that's hyperplane H dash, so parallel, they have the same normal, in a sense. So they're two normals, they're collinear. Yeah, they lie along the same line. Now it's possible, when I say lie upon the same line, it's possible that the second normal might oh, you can't see it, but in the opposite direction. That's also a possibility. Collinear, so long as the two lie along the same line. All right. Okay, so if you construct from talking earlier sessions, if you construct the coefficient vector from the hyperplane equation, so in this case, like here's the equation of the second hyperplane. So to construct its coefficient vector, the first component would be 4, and the second would be -5, and third is 2, and the fourth is 1. So the vector of 4, -5, 2, 1, that's the coefficient vector of this hyperplane. And we proved earlier that that coefficient vector is the normal, meaning it's the vector of of this normal. The normal, remember, is just the vector that's orthogonal to any vector lying, any straight line, directed line segment, lying in the plane, in the hyperplane. So this vector and that are orthogonal. You just see in a three-dimensional space, this vector and any vector lying in the plane will be at 90 degrees to each other, and hence the dot product will be 0. And by definition, when the dot product of two vectors is 0, those two vectors are said to be orthogonal. A bit of revision. All right. Okay, so the normal for this hyperplane will be 4 -5, 2, 1, and that normal will be the same, or maybe a sign change or an expanded coefficient. The normal might be a bit longer or shorter, but it's just effectively some constant times the normal of this one. And the normal of this one, it's just its coefficient vector, which is 4 -5, 2, 1. Okay, so we know by taking the coefficient vector of this second hyperplane, we know the normal of the first one. It'll just be some constant, I don't know, k times this one's normal, right? So we've got we know the normal, the coefficient, the coefficient vector of h. It'll be just k times the coefficient vector of this one, which is 4 -5, 2, 1. And what else do we know? And we know that this point P, and here's its vector, lies on this surface. So that should be, given the normal of this surface, and a point that lies in or on the hyperplane, that's enough to specify, like, so here's h, the hyperplane, and you know it's normal from the coefficient vector of h dash, the second one, and if you can position, and you know a particular point that this hyperplane lies in, so it's where the tip of my finger, just here. Well, that positions where this hyperplane has to be, so it'll be there with this point lying in it. Okay, so if you know a point lies in the surface, and you know the surface is normal, that pins down, that specifies the hyperplane. Okay, done a bit before. So the hyperplane equation for h for hyperplane will be of this form, with the same coefficient matrix as this one. So 4 -5, 2, w. Okay, but you don't know what this k is, so we'll just put it. We don't know what it is. We'll just call it k. It's for the moment an unknown. But we do know that this hyperplane h, whatever it is, this point here lies on the surface. So this point is a solution to this equation. Because what are all these x, y, z? They're all infinite number of them, and in fact an uncountably infinite number of points lying on the surface. And these are actual values for these four. They are so-called solutions to this equation. I mean that's what the equation does. It just specifies all the potential points, or vectors x, y, z, w, that lie on the surface. So we can plug in these numbers here, x, y, z, w, and we know that point lies on the surface. So this vector here is a solution to this equation. Well, these are concrete numbers, so just plug them in. So we will get a number, concrete number, on the left-hand side. And since this is an equation, equal, therefore whatever's on the left-hand side will determine what k should be. So let's do that. So just plug in this value here for your x, y, z, w, and here it is. So 4 times x, so it would be 4 times 1 plus minus 5 times y, so minus 5 times minus 2, and 2 times z, so 2 times 6, plus 1 times w, so 1 times 5. So plug these all in, and so you'll get 4 plus 10 plus 6 plus 5 equals k. And what is this? 14 plus 11, that's 25. So k is 25. Okay, so here's your equation. Here is the hyperplane equation for h. So it'll be this, and now we know what k is. It's 25. So we just plug it in. There's the equation. Okay, so that's solved. End of. No, it's not a theorem. It's just a result. Okay, next question. And this will be the last question for this chapter, the last solved problem talked about in this lecture, in this chapter 1, lecture 1. So 133. Now we're talking now not a plane but a line. Just a straight line. So a one-dimensional line, if you like, but it's in hyperspace, n-dimensional space. We're talking about real. We're talking reals, are we? Yes. Yeah. And now to keep it concrete, so get the general idea. Let's talk. We're talking in the context of, say, R2. So just two-dimensional real space. So the vectors in this space are real vectors, meaning that their components are real numbers. All right. Now, so imagine this straight line here, and we're told that a particular point P lies on the line. So if this is the origin of your coordinate system, this vector from the origin to point P that lies on the line, it would be this vector here. So from here, this arrow. So from here to point P. Okay. Now, draw a second vector, call it U, and make it parallel to this line. I mean, this is a given line. It's just there, right? So create this second vector, call it U, and it's parallel to this line. Now, what we're trying to do is try to find an equation for the line. Now, earlier, a couple of questions, we were finding hyperplane equations. So an equation for a plane, a flat surface. But here we're talking about a line. We're trying to find an equation for the line. Well, watch. Now, this vector from, I call this point x, it's just a general point, any point on the line, on this line. So the vector, or the arrow if you like, from the origin to this point x here, so that it would be this arrow here. Now can you see that this vector here from the origin to x is equal to this vector plus this vector, right? It's just vector addition. So this vector here is equal to this vector plus that vector. Okay, well let's express. So this vector here, just call it x, and put a little wiggle here to indicate that it's it's a vector. And what is x? Well, this vector here is equal to this one. Well, what's that? Well, that vector is just p, right? That's your point on the line. So it's vector p plus some constant, call it t, of u. Now remember, a vector, the starting position of a vector is irrelevant. Like so long as this length here is equal to this vector u, then this vector and this vector, since they're in the same direction, so they're parallel, and the same length, norm if you like, then they're the same vector by definition, because you only need two properties to specify a vector, its length and its direction. Now that's the definition that's the very definition of a vector from the physicist's point of view. Okay, as an arrow. So okay, so this vector x here, so that's from here to here, is equal to this vector, which is p plus this vector here. Well, what is this vector? Well, it's going to be some constant times u, right? Because it's parallel to this one. So let's call this constant just t. We'll say t1 here. And so vector x will be vector p plus t, or t1, vector u. So x equals p plus tu. That's your general formula. And now by varying t, you will get, say you make t larger, well that's just making this vector from p to x longer, right? If you multiply a vector by a constant greater than 1, you just make the vector longer. So as t, assume t is greater than 1 now, so you just extend the length of this vector. So by increasing t, your x just moves up the line. Okay. Now if t is negative, well you're going the other way, right? That would make u here sort of negative. So it's the oppositely directed. So you'd be going this way. Okay. But you now have a general formula for the equation of the line, and it's of the form x equals p plus tu. That's it. Now if you want, that's in vector form. If you want the component form, if you want the ith component of vector x, it would be of this form here, right? So the ith component, so xi will be vector p. Oh, by the way, we're using a notation here. This is just shorthand for an n tuple, right? These AIs are just the components of the vector p. So the ith component of p would just be ai, suffix I. So the first component would be a1, and the nth, if you're in n-dimensional space, the nth component of this point p would be a n. Okay? Alright. Now this t is just called a parameter, because in the nature of a parameter, what is it? It's some number that can vary, and if you give it a concrete number, that will specify something. In this case, it will specify x, because this is given, and as t changes, x will change. So t is just called a parameter, and the list of all these components formulas, that's called the adjective of parameter is parametric, and it's a parametric representation of your vector x here. And this this is a formula for the component, the ith component of your vector x. Right? So this is just the ith component of p. Here's your p here, and this is just the ith component of your vector u. That's here. That's a vector that's collinear with your line. Okay, so u and p are given, and so the equation of the line, it'll be of this form: p plus tu. Hope you follow all that. All right. So just summarizing a bit. So a parametric representation is just a list of these component formulas. You'll have n of them in general for an n dimensional space. So you'll have n of these where I ranges over 1 to n. All right, now an actual question. So the first part. So you're given we're now in R2, the two-dimensional real space, and you're given a point whose coordinates are just 2, 5, and you're given a vector that's collinear with the line, so be u here. This u is parallel to this line, remember, and you're given this vector. Its components are minus 3, 4, and you're asked to find a parametric representation. In other words, you're asked to find this list. You'll have, well, we're in 2 dimensions, so I will range from 1 to 2, so we'll just have 2 equations like this. So we'll have x1 equals a1 t u1, and x2 equals a2 t u2. So we just plug in the value for a1 and u1 and a2 and u2, and we have it. That's the parametric representation, just the list of these component formulas. All right, well, let's do it. So here's your general formula. So vector x equals vector p plus t vector u, and that implies that the ith component of that will be here, which is here, we go 3 times, and that implies, so let's find x1. Well, x1 will be a1. Well, what's a1? A1 is just the first component of your point P, which is 2. Okay, so your a1 here will be 2 plus t, and the first component of your u, well, that's here, so that's minus 3's. So you'll have t times minus 3. So just rewrite that slightly. So x1 will be 2 minus 3t. So no, how about x2? What will that be? So x2, it'll be a2 plus t u2. So what is a2? It's 5. So here's your 5 plus t, and what's u2? It's here, 4. So 5 plus t 4 equals 5 plus 4t. So you have the second component of this, and you have the first component here of this, and those 2 components, given we're in 2-dimensional space, R2, so we now have our parametric representation. It was the list of the component formulas, 2 of them. x1 is that, and x2 is that, and that's your list, and hence that's your parametric representation. I'll stop there. Ciao.